this one more.
That's how it was before. I mean, that's the problem. Is you can't really see. Yeah. There might be more switches up there. I don't know. All right. Well, yeah. When we leave Mendenhall 291, all bets are off. Okay. Well, it's my pleasure to welcome you to the technical lecture as part of the 79th annual Bownocker lecture series. Today, I am happy to introduce Dr. Emily Brodsky, who is a renowned geophysicist whose groundbreaking research has significantly advanced our understanding of earthquake mechanics. Dr. Brodsky is a professor of earth and planetary sciences at UC Santa Cruz. She earned her bachelor's from Harvard, her PhD from Caltech, and her research addresses processes that trigger earthquakes and the constraining forces and processes that occur inside fault zones during slip. Her recent work includes important findings about earthquakes induced by human activities such as hydraulic fracturing, wastewater disposal, and geothermal wells. Dr. Brodsky has received numerous awards and honors throughout her career, including the inaugural Charles Richter Early Career Award from the Seismological Society of America, the James McIlwain Medal from the American Geophysical Union, the Willard Award for the Geological Society of America, the A.G.U. Gutenberg Lectureship, the Price Medal of the Royal Astronomical Society, and in 2023, she was elected to the U.S. National Academy of Science. She has published over 150 peer-reviewed papers and has presented over 150 lectures in 30 states. I have to rapidly change these numbers because every day there's more, they go higher. And 30 states and 13 countries. Her work has been featured in many major media outlets. So today we're going to hear a talk entitled "The Variability of Stress and What to Do About It." Please join me in giving another warm welcome to Dr. Emily Brodsky.
Thank you. Well, thank you, Ian, and thank you, everyone, for a really great visit. I'm very honored to be giving this lecture, and I really enjoyed my time here and learning about what all of you do. Last night, I talked about the earthquake problem in general. Today, it's going to be perhaps slightly more philosophical, talking about the variability of stress and what to do about it. And this work is based on, this talk is based on the work of a number of slugs, current postdocs and students, Will Steinhardt, Gaspar Farge, Doron Murad, Wian Grau, who's recently graduated and now at Caltech, and Alba Rodriguez Padilla. I don't know why I ended up saying not at Utah State. She is at Utah State now as faculty. She was never formally a student, but spent an awful lot of time with our group. So let's start at the beginning. If we're going to talk about earthquakes, it's useful to start by framing the problem in terms of basic physics. Earthquakes happen when the stress on a fault accumulates and ultimately hits some failure strength, probably friction. And then that threshold, the strength of the fault, allows the stress to be released in an earthquake. The fault slips forward, and then the cycle repeats. And we spent a lot of time last night discussing this earthquake cycle, for those of you who are able to make it. And I made the case to you that, this kind of simple picture of stress accumulate, strength, and repeat would be very predictable if that were all there was to the story. But as it turns out, earthquakes and fault systems are more interesting than that. Strength can vary over time. Stress accumulation can vary, stress release can vary, and so as a result, we have significant lack of predictability in the system. All right, so what do we do about all that? Well, I mean, we carry on because we're scientists, and even if this Earth is complicated, we should still be trying to develop natural experiments and anticipating what comes next. That's how we do science. And so, for instance, one exercise that is commonly done in earthquake studies is to forecast aftershocks. One of the ways we go about this is to calculate the stress change from one earthquake and how it's able to influence future earthquakes, the aftershocks after an earthquake. So the idea here is, an earthquake slips, it releases stress wherever it happens, and off the ends of the fault, it might increase the stress off the ends of the area that just slipped, and around it, it might increase stress. So there's a pattern around an earthquake of places where faults are pushed closer to failure. Those are red here. Around the 92 Landers earthquake, this particular calculation was done. And where it's released is in blue. And then in this review paper by Jean Hardebeck, she notes that most of the earthquakes from Landers happened in the red spots, and ridge crests, most of them happen in the red spots, so we're going to declare success, right? And yeah, sure, maybe there are a few earthquakes over here in the blue area, but, nothing's perfect. Stress varies in the crust. Maybe those faults were just totally ready to go anyhow, and even though the stress decreased, they went anyhow. Who knows? Could be. Good enough. So my point here is the variability of stress on faults, that some faults are just ready for failure, some faults are very far in their cycle from failure, limits to some extent our ability to predict. The problem gets worse when we start talking about induced seismicity. So this is human-made earthquakes. Humans do make earthquakes, by the way, in case, you study climate for a living and you haven't thought about it before. Humans can make earthquakes. Generally, we make earthquakes whenever we, human beings, inject fluid in or out of the ground is a good way to make earthquakes. If you bring large masses in and out of the ground, like in mining, also a good way to make earthquakes. There are a lot of different ways to do it. And this sort of rose to a level of public concern in Oklahoma in the early 2010s with large-scale fracking came in. And this is a particular place in Oklahoma where there was large-scale wastewater injection. And all those blue triangles are wastewater injection wells. And you can see that the water was injected, it increased the stress locally, pushing towards failure. That's what's indicated by the red. And it made a bunch of earthquakes. But interestingly, it also seemed to have made an earthquake around 30 kilometers away from the edge of the injection zone in Fairview, Oklahoma. Actually, it also did another thing set in Woodward. So that's a little bit weird. It's like you're pumping water here in Columbus, Ohio, and I don't know, what's 20, 30 kilometers away from here? A third of the way to Cleveland, right? You made an earthquake. Well, I mean, the stress did increase here in the direction of failure if you actually calculate it. And so it's plausible that injection affected it. And because it's a big injection field, its sort of footprint on the Earth and the stress field around it is a large finite source. So this is actually just one source on the way. So that it's kind of okay physically. But why Fairview and why not over here or over here or over here? Well, because the Fairview fault must have been really close to failure. And so you just hit it with a teeny bit and away it goes. So physically, that's a reasonable explanation, but it's not a very satisfying answer to the people of Fairview, Oklahoma on why them. And so my point here is earthquakes often occur at discrete and potentially unpredictable locations because of this variability of stress. So what should we do about it? Do we just give up and say, hey, we're going to just be wrong a lot of the time, or we're just going to miss it, or we're simply not going to know which faults are near failure? Legit strategy, move on to glaciology, but maybe we can do better than that. One way we can do better than that is to start thinking a little bit about this, what is inherently a statistical problem in terms of statistics or distributions that are observable and that we can measure. And so what Thomas Goebel did here with me when he was a postdoc was to look at the density of induced earthquakes at various distance from relatively isolated wells, where there was some injection, not like that big complicated field, but where there's some one well sitting by itself somewhere. And he noticed that there were kind of two populations of this density of earthquakes as a function of distance of wells. So the ones that fell away gradually to some quite distant locations, maybe as far as 10 kilometers away. And then others that were much more compact structure, compact distribution. As it turned out, the red-orange ones here, the ones that fall away gradually, were all relatively shallow injections in the sedimentary structure. The blue ones were deeper injections into the basement. And so one can start to think a little bit about physics. What we think is happening here is that we have a pore-elastic field building around the injection for shallow injections that are relatively soft rocks where we have good coupling between, well, high porosity, so we have good coupling between the solid and the liquid, and we're able to create a halo of elastic strain around the injection, creating a well-defined distribution. And whereas the deeper injections are simply a pore pressure increase in a relatively compact zone with not so much solid coupling, and are creating a different style of seismicity. Great. That might be a useful insight for thinking in general how to proceed on mitigating induced seismicity. Somewhat counterintuitively, perhaps deeper injections are in this sense safer, at least have a more localized zone of danger than shallow ones. And more importantly, that the pore-elastic field is a really important part of this problem. And perhaps more philosophically, that distributions are a really good way to move forward on the variability of stress in the Earth. That there's some faults near failure, some faults far away, but their distribution as a population can be well defined in a way that lets us do something useful. Okay, so the game then becomes, what are the observable distributions of either stress or strength in the Earth? And that's not trivial. I mean, I said, it's hard enough to measure one thing in the Earth ever in situ. How am I going to be measuring these distributions? So I just gave you an example on density of earthquakes. And now what I'm going to run with it a little bit. I'm going to try to give you a few different examples of observable distributions of stress, energy, and strength. By the way, I know it's not the culture here to interrupt the speaker, but I come from some pretty obnoxious institutions. And so feel free, I'm totally cool with it. And I'd much rather you interrupt me and get unconfused in real time rather than sit there and worry about it and miss the rest of what I say. So interrupt as you see fit. Okay, so one way to measure the distribution of stress in the Earth is to look at when one earthquake triggers another. This is an example I brought up last night. Gonna refresh, and for those who weren't there, is we do have this phenomenon known as dynamic triggering, where one earthquake triggers another via the seismic waves. And we know this exists because we see it. Here is an example of seismic waves arriving in Montana from Alaska. These are nice long period surface waves that can travel all the way around the Earth. And at the time they arrive in Montana near Yellowstone, these high frequency waves start popping off of local earthquakes. If you zoom in on any of these, you can see that they have well-defined PNS. They really are earthquakes. You can locate them, you can count them. And they're really starting right at the moment these surface waves arrive in Montana. So it's pretty blindingly obvious evidence. We don't often get blindingly obvious evidence in earth science, but I think this one's clear, that the seismic waves are doing the triggering. So by measuring the rate of earthquake rate change in response to these amplitude of seismic waves, these waves are, I don't know, 0.5 centimeter per second in peak ground velocity. So that's right about here on this graph on the x-axis. We can measure what the resulting rate change on average. Oh wait, this is in centimeters per second. That wasn't looking right. 0.5 centimeter, there we go. That makes much more sense. What the resulting rate change is, and calibrate that over a large population of earthquakes. These nice, blindingly obvious examples are pretty rare, I will admit that. But what we can do is take all the seismograms, all the earthquakes in the world, and that happened over some period of time, and a really nice catalog of earthquakes like Southern California, and measure any biases in the timing of earthquakes relative to that moment of shaking. Do the ones afterwards come a little bit sooner than they should have relative to the average inter-event time? And by doing that kind of population stacking, we can measure these very small rate changes. We, in the sense of Nicholas van der Elst, who was another former student. And so when Nicholas did this, he got this nice measurement of earthquake rate change as a function of peak ground velocity. And we interpret this in terms of a distribution of in situ stress in the Earth. That if you hit the ground with just a little bit of velocity, a little bit of ground shaking, you push over the faults that are very near failure. If you hit it harder, you being an earthquake, more of the faults that are even further from failure are allowed to have earthquakes, are pushed over the edge, over their strength. And so overall, this distribution, this measurement, totally observable measurement of how many earthquakes you get as a function of incoming ground velocity, which is proportional to the strain or stress in the waves, is measuring the in situ distribution of stress in the earth. How many faults are near failure? How many faults are far from it? And actually, you could see it's a pretty straight line here on this log plot. That means that since this is a cumulative distribution, if you hit it with a large stress, everything from that stress on up, it gets failed, everything gets swept clean. So that is actually consistent with a uniform distribution of stresses on faults. That there are just as many faults that are a Pascal from failure as there are 100 Pascal for failure at a time. So the faults are kind of randomly distributed over their cycles, which is a pretty neat thing. Didn't have to be that way. Could have been synced up, could have been not synced up. Okay, so triggered earthquake rates reflect a well-defined distribution of stress from failure that is observable. We don't have to give up on the variability of stress in the earth. We can measure something. Second example of an observable distribution. This is a measurement that Alba Rodriguez Padilla, quite recently on available energy. And let me walk you through it a little bit. It's a little bit of a complicated argument. But what she did with her advisor, Mike Oskin at Davis, was to look at faults, propagation on faults that had really nicely well-mapped fault traces of large-scale strike-slip faults that broke the surface. And she looked in particular at when did the propagation cross across stepovers, when one fault steps over to another fault. Does the earthquake keep going or just get stuck at this stepover? And she also did bends and double bends. I'm just showing you stepovers. She did a bunch of different kind of barriers that might exist in a fault network. And what she found empirically is that when that there was a population of ruptures that passed through stepovers, and that was more or less limited at right around a kilometer width. And then after about a kilometer stepover width, in general, ruptures didn't make it through. So that's a very tight distribution in a way. It's almost a delta function of ability to get through versus not ability to get through. Now, I keep saying it's a distribution of what? Whether or not a rupture is able to propagate, whether or not a fault, an earthquake can keep going versus stop, is determined by the available energy, the available elastic energy that feeds that fracture and keeps it moving. Whether or not an earthquake starts is determined by stress versus strength. Whether or not it keeps moving is determined by how much energy there is available to feed it. And so what this is saying is that in all of these cases, there was kind of enough energy to keep it going if the stepover is less than about a kilometer, and not enough to keep it going if the stepover is more than that. So in this case, the distribution is, practically a delta function. There actually is a number. We approached it as a statistical problem, but there is a number about available energy, at least at this scale in the crust, that is able to keep propagation happening. The probability of rupture arrest at barriers reflects a well-defined distribution of available energy. All right, third example of a distribution. Earthquakes happen when stress overcomes strength, so we better think a little bit about what we can use to measure. What is there that we can measure out there that's going to tell us anything about strength in real systems? And I'm going to argue to you that fault roughness is a really great way to measure strength. And when I first say this to people, they kind of just sort of stare at me blankly, like I just said, I don't know, croaking frogs is a good way to predict earthquakes. It doesn't seem like a sensible statement. But bear with me for a second and let me explain what I mean. Fault roughness is something we can measure. We can go out to an exposed fault surface and measure its topography, measure how big the bumps are at various scales. It's not that complicated. You could take a ruler and measure it, or a LiDAR, or a drone, or something, some technology, and measure it. And when you do that, you find that there are bumps at all scales, that faults in general have smaller bumps at small scales, smaller amplitude bumps, and at large scales have bigger bumps, like many natural surfaces. When an earthquake happens, when one side slips past another, those bumps need to get past each other somehow. And so one bump slams into another, and if the bump is small enough, it squishes down. So, this was my fear of switching to from a Mac to Windows. We have a little bit of a notation issue here on the symbols. But what I'm trying to say is that there is an elastic strain that you get by pushing down on a bump to let it slide past another. Shear strain in general, the definition of shear strain is displacement in one direction accommodated over a distance in the perpendicular direction. Okay? And so, therefore, the shear strain that would be required to flatten this bump is the height of the bump, h, which has to get squished and accommodated over a distance L, which is the length of the bump, the wavelength of the bump. So the shear strain is proportional to h over L, the aspect ratio of the bump. If that shear strain is too big, if the bump is too steep, then that strain can't be accommodated elastically anymore. It has to squish plastically or fail, get decapitated, something. So that needs to be less than a yield strain in order to be preserved. The aspect ratio h over L needs to be less than the yield strain in order to be preserved on the fault surface. We're always making new bumps. Faults are complicated things, always creating roughness. And so my hypothesis here is that this aspect ratio is always pushing up against the yield strain limit, and actually the preserved aspect ratio in real faults is a useful measure of the yield strain at multiple scales. Because I said there are little bumps, there are medium bumps, there are big bumps. And so as this aspect ratio changes with scale, we're measuring the change of strength with scale. So the idea is that we go out there and measure the topography of faults. I've showed here as power spectral density, which, if that's not familiar to you, just think about it in terms of these red lines, which are lines of constant aspect ratio. And at different scales, the data either has very steep bumps at small scales or smoother bumps at large scales. And I'm saying, well, measure the aspect ratio as a function of scale, and let's interpret that as yield strain as a function of scale. So now we got it. This is a way to measure scale-dependent distribution of strength. It's a way to get measurements out of the laboratory into the field scale. One thing I've been working on quite a bit recently is how to validate or not, as the case may be, this hypothesis. Valère Lambert and I just submitted a much more rigorous mathematical treatment of this, of scale-dependent strength of rough surfaces that goes past this cartoon view of definition of shear strain. Turns out that a more rigorous mathematical analysis by scaling law wasn't terrible. We're also, Chris Tom has measured scale-dependent plasticity hardness by doing indentures in the lab. And so far, so good. So that is another way to proceed. That roughness reflects a well-defined distribution of strength. And so my bottom line here from all three distributions is that these well-defined distributions, I keep using that word, well-defined. That means that you can measure it in lots of different places and you keep coming up with the same thing. And it's not this different everywhere you go. Distribution of strength to failure, available energy and strength actually exist in the Earth. Yes? I'm not sure I can bring my mental state back to before I saw this plot anymore, but I do think that in general, we think rocks are weaker at large scales than small scales. That is generally true, right? We don't build skyscrapers out of rocks for a number of reasons, one of which is that they are much weaker at large scales. And that weakness is a well-known intentional failure. It should be the same in shear failure, but we haven't really had a lot of ways to measure it. The square root is actually, you can make an argument based on fracture mechanics that might suggest that this was a pretty reasonable way to think about the problem, that the stress intensity factor should fall off a square root of scale. I'm not sure that's the right argument for this data, but such as we understand the scale-dependent theory, certainly it should go in this direction. I think the direction is clear. Whether or not you can reproduce the exponent, who knows? That's why we make observations. Good question, thanks. And thanks for breaking the ISO questions. Anything else? All right, so we have a bit of, it's a bit surprising in a way that these well-defined distributions actually do exist. It's surprising that this succeeded at all as a strategy. And why is that? I don't know, but I have a speculation. My speculation is based on my understanding of frictional systems. Frictional systems, like rocks in contact, are also granular flows, that is, ground up pieces of rock that in 3 dimensions that flow past each other, like a pile of sand or till or fault gouge. All of those are landslides. All of those systems share a very important feature in common, which is that the stress is non-uniform on the system. All of those systems adjust themselves so that the stress is distributed in a very certain way to support the load. Microscopically, the way friction works is in between two surfaces, there are teeny tiny contacts that are getting squished and deformed by the weight of the material on top, and that the real area of contact between a surface is proportional to the load. The picture I've left up here is a photoelastic experiment that Duran Murad has been doing in my lab. It's a visually beautiful, stunning experiment where these are little plastic discs, and when you put polarized light through them, they light up when they're stressed. So what the bright force chains are that you're seeing running through it, that's where the stress, the weight of this plate at the top is being supported. And you can see not every grain has the same weight on it. Some have different, some are stressed and some are just sort of, I don't know, freeloaders, standing by, watching the others do the work. Okay, we call those spectator grains. And actually this distribution of stress is surprisingly consistent as we move across 3 orders of magnitude in velocity, spinning this device. We are very far from the first people to have established that force change exists in granular matter. I just want to be clear about that. People have known that for a long, long time. What our new innovation here is actually being able to look at it as a function of velocity, which nobody has done before. But my point for the purpose of this talk is that well-defined distributions exist in frictional systems. It's an intrinsic feature of frictional systems. So maybe we shouldn't be so surprised that the Earth is cooperating in this way. Yep.
You're spinning it?
Yeah.
So there's also an acceleration. Is that analogous to what you...
We have not done transient experiments yet. It's on the list. But what we've been doing with this, and it's a different talk for a different day, is spinning the bottom at a constant rate. What? Yeah, it's 2D. So this is a 2D discs in a cylinder on the outside, in a thin cylinder. Whoops. And so we can run it at a constant rate, and then we can measure the distribution of stresses. And actually, the big story of this one is that the distribution of stress is velocity independent, and also that we can predict the frictional behavior through some local measurements, including the average kinetic energy, the average vibration of the grains. You let a seismologist at granular flows, and I start looking at how the seismic waves interact with the flows. And that actually turns out to be an important part of the rheology. But that's an aside, and I am really happy to talk about this after the talk. I'm very much on a granular flow kick right now. But I want us to sort of stick to the subject here about distributions moving forward. So we have well-defined distributions in the Earth. Maybe philosophically we might speculate that they're expected because these are fundamentally frictional systems, and frictional systems have heterogeneous stresses and organized heterogeneous stresses. And so now, how do we use them? Now that we have these distributions, what can we do with them? Are they useful? I mean, if we're not doing useful things, why are we doing science? How do we use it? And so now I'm going to give you 3 examples of 3 very different use examples of distributions. The first one is to measure changes. In the upper right is another version of what was Nicholas's figure a little while ago of the earthquake rate change as a function of the stress of the incoming waves. But we undid this at single stations. So she took a single seismometer rather than a catalog of earthquakes and said, you know, we can measure the ground motion at that seismometer. That's what seismometers are designed to do. And we can also pick the local earthquakes within a certain radius based on P minus S time of that seismometer and look at how rate changes change very, very locally as a function of velocity. And because we start to see these well-defined distributions, even if at every single station we don't quite have the full distribution measured and every single velocity measured, we can kind of extrapolate to a common point. So we can ask what the spatial and actually temporal variations are of triggerability, how easily a area triggers, based on incoming seismic waves. You know, is the line down here, or is the line up here, or down here for a given seismometer? So here's a map of triggerability in Southern California. I swear to you, the Earth is not made out of Southern California, but it is a nice seismic network to work with. And triggering intensity at various stations. This is before the 2019 Ridgecrest earthquake. And you can see there's some variability. Some stations are more triggerable than others. It's a map. After the Ridgecrest earthquake, triggerability changed dramatically. So we've left out 1 month in between. 1 month after Ridgecrest, it's just all piles of aftershocks. Let's not look at that. Let's wait and then look in the ensuing years. And what we find is that basically Southern California turned blue, became less triggerable. Well, that's cool. It suggests that maybe this big earthquake or moderate earthquake, not the big one really, this moderate earthquake shook Southern California, activated all faults that were already near failure, swept them clean, and then when it was all over, what was left was probably much less prone to triggering. And it's an observation you could never make on a single measurement, but you make by capitalizing on that distribution. That's fun. So a distribution-based measure suggests that Southern California became less triggerable following the magnitude 7.1 Ridgecrest earthquake, likely due to an exhaustion of faults near failure. Let's try another example. Here, let's move to Japan. Earthquake people. Either they do Southern California or they do Japan. This is a truly magnificent observation. What you are looking at is over 20 years worth of data of tremor along Nankai in Western Japan. Here we go. And so what tremor is a little bit of noise that faults make that isn't quite an earthquake. It's generally associated with slow motion of the fault, slow slip or slow speed earthquakes. And in Nankai, it is at the down dip end, 40-ish kilometers depth, below where we expect a big earthquake. And the big discovery in the early 21st century was that tremor existed on these big subduction zone earthquakes, subduction zone faults, and was shockingly regular. And when it was first discovered, people saw a few cycles and said, that looks pretty periodic. But isn't it a miracle when we have 20 years worth of data? Long-term observations show there are real systematics here. The y-axis here is distance along strike, and so what you can see is there are areas where the tremor is very, very regular, maybe a year, maybe less intervals. There are areas that tend to synchronize together, have tremor together. And then there are areas that are pretty ratty looking. I mean, this bottom bit here is, right? That's my technical term for it. It's not particularly well organized. So what Gaspar noticed is that the tremor is anti-correlated with where there are regional earthquakes. The red dots are earthquakes. Ooh, I gotta move that talking thing. Maybe if I stop talking. Can I move it? Because you gotta be able to see where the earthquakes are. Aha! All right, doesn't matter. I almost never put anything on the left side of the slide. Red dots are earthquakes that are either in the crust or inside the slab, so not in the same place as the tremor. Black is where the tremor is, red is where the earthquakes are. And what I want you to notice, oh, now my clicker stopped working. That's what I get for playing with it. Is that here we go. The reds, lots of red dots are where the tremor is not particularly well synchronized, where you have these ratty bits, maybe around this central stripe here, or at the bottom of the graph is where there's lots of red. And where you have these beautiful synchronized pieces, like right here, there's very little red. There are very little earthquakes. So the observation is more earthquakes, more desynchronized tremor, less organized tremor. And the same thing turns out to be true in a number of subduction zones around the world. Conspire put together a compilation and found that although there are plenty of complicating factors and complicating trends within each individual subduction zone, as a group, there is some systematics. And probably the most fair way to describe this kind of messy looking data is that there's nothing in the upper right-hand corner, right? That I mean, I wouldn't want to be fitting a trend here, but if you have really a lot of regional earthquakes up here, you can never have very synchronized zones. Doesn't happen. So then, why is that? What Gaspar suggested is that in the absence of any regional seismicity, tremor patches tend to like to synchronize with each other. One hits the other, hits the other. You kind of get a domino effect if you're stressing one and it fails. That pushes the nearby ones to failure, which pushes the nearby ones to failure, and you end up with a synchronized, locked cycles. So this is a very certain kind of distribution, a very compact distribution of stresses. So he's using distributions sort of as an interpretive tool here. You think? Awesome. Thank you. Whereas if you have regional earthquakes, that has a tendency to perturb the system and push each individual tremor patch locally out of synchronicity. It's not just waiting for this domino effect, it has something else motivating failure, and we end up with a more distributed system. So, the observation here and interpretation is that stress distributions and hence synchronization are influenced by regional earthquakes. This implies a very deep connection between the system. Crustal earthquakes that have nothing to do with the subducting slab, in some sense, are actually affecting the cyclicity on the slab through this interaction. It's all one system. I was hoping to put accepted there today. The final revisions just went in yesterday, so I think we're done with this paper. You can see by thinking about the system in terms of stress distributions, you start to realize why you might get different kinds of behavior. All right. My last example of the utility of this distribution approach comes from the lab. And my point here is going to be that stress distributions, when you're thinking about heterogeneous stress, create behavior that qualitatively cannot be accessed through a simple uniform system. You actually must, it's not an option, you must think about the system in terms of heterogeneous stresses. And I think that's best illustrated by this experiment that Will Steinhardt put together, which is a transparent rubber device where he can image earthquakes in the lab. And so it's sort of squishy, and he puts a little layer of sand between the two sides of the faults. And that layer of sand makes it, can I call it homogeneously heterogeneous? That there are stress variations kind of everywhere. And what that does is allow a non-uniform system. It makes it so if we had tried to make a perfect uniform set of fault blocks, there would have been some little imperfection somewhere, some little scratch that would have controlled the whole behavior. But by making it homogeneously heterogeneous, we actually have a much better controlled system. And he's done a number of different experiments with this. Most recently, he started looking at the sequence of locked and slipping patches. Now, can I get, yep, I got, the movie's working. All right. So blue is slip and red is loading. And so this is fault's about yay big, but because it's very squishy, when one patch slips, the whole fault doesn't slip. It's just locally slipping. And then other patches are locally loading. They're locked. And so there's a catalog of slip events. And interestingly, there's also a catalog of locking events that move along in space and time. This is unwrapping the data where the x-axis is time and the y-axis is position along the block. And these blue patches are slip events and the red patches are locking events. And so what Will did then was, first of all, notice that there are transient locking events. It's actually not typically the way we think of a fault. We typically think of a fault as all locked and then slipping locally, but actually it's not all locked. Some of it's locked and some of it's not locked. And then investigating the relationship between the two catalogs, that the locking events can be predictive of both the timing and the location of the next slip events and are different distributions in space and time relative to a random catalog, which are the green reference curves here. So large locking events are predictive of the location and timing of the next slip event. And this only happens when you have a heterogeneous distribution. If you started with a uniform block, you never would have seen this. So given that we expect real faults to not be uniform, we might expect that we should be looking for these locking events and the similar relationships in space and time to slip events. Will also took on the issue of stress drop, and this might be a slightly more technical issue, but bear with me. Stress drop is the amount of stress change that happens in an earthquake. It turns out to be something that we can measure from seismograms, and so seismologists like stress drop a lot. Seismologists can't measure absolute stress. If you push on this table slowly, and just like if I just lean on this table, I can't measure that from a seismic wave, from vibrations. But if I hit it transiently with an earthquake, I can measure that stress change of my hitting with the seismic waves. That's what the amplitude of the vibrations is sensitive to. So stress drop is kind of an important quantity in seismology because it can be measured seismically. And so stress change during an earthquake is expected to be, well, proportional to the friction at the beginning of the earthquake minus the friction at the end of the earthquake, the stress change on the fault. And friction in general changes with the weight of the rock on top of it, right? If you put a heavier object on this table, it has more friction, harder to make it slide than if you have a lighter object. Okay, so if that whole picture I just drew for you is correct, then stress drop should increase with depth. much to seismologists' chagrin, that is not the observation. And it's been a bit of a mystery for, I don't know, 50 years, why stress drop does not systematically increase with depth. The most common explanation for it is that maybe the pore pressure, the fluid pressure in the earth also increases with depth, and they magically balance each other out, and and therefore there's no problem. That the water is basically supporting the rocks. So what Will did was take his transparent rubber and sand, no water in the picture, pretty simple system, and measured the stress drop on his earthquakes. And he measured it in various conditions, pushing on the little center of it with the disparity, a little bump, or not pushing on it, putting thick sand, putting thin sand, and the stress drop sort of varies from event to event. But on average, as he increased the normal stress going across any condition, the stress drop didn't change. So despite that, I just totally walked you down the garden path, didn't I? Despite that expectation that you push harder on the surface, stress drop should increase, in this heterogeneous system, that turns out not to be the case. In fact, he worked pretty hard to try to make this result go away. You can see that from the number of data points on the screen. And the only thing he could do to make it go away was make a smaller sample. So if he cut down the top block to a teeny tiny 2.5 centimeter sample, suddenly the stress drop increased with the normal stress again. So what that is telling you, our interpretation here, is that as long as you have a big enough system that when you have these slip events, they stay contained within the fault and don't hit the sides of the fault, then you start creating this naturally heterogeneous stress state influenced by all the prior history. And in that system, the stress drop is totally normal stress independent. Really, you have a few strong spots, you have some weak spots. They've organized themselves in a way that creates a stress drop that is normal stress independent. But as soon as you get to something that looks a little bit more like a slider block, a little bit more like my brick yesterday, where the ruptures hit the edge of the system, that property goes away. And so normal stress being depth independent is kind of a natural consequence of heterogeneity. It just happens. No pore pressure, sorry hydrogeologists, no pore pressure required, as long as you have a natural stress distribution influenced by the prior history. So that's a qualitatively different behavior. So to finish it up, what I have told you today is that we can measure the distributions of stress in various ways in the Earth. We can measure we can measure distributions in various ways on Earth. We can measure the stress from failure, relative to failure, by dynamic triggering. We can measure available energy from ruptures, the strength from fault roughness. All of those are actual observables. And the Earth does seem to provide us with some pretty well-defined distributions, possibly because it's a frictional system. Maybe that's the way it works. Once we have these distributions, we can use them to examine changes like the reduction of triggerability in Southern California post-Ridgecrest, to interpret observations like the desynchronization of tremor by regional earthquakes, and to explore behavior that qualitatively cannot be reached by a uniform system, like locking events and also stress drops. So finally, I guess I want to point out that to do distributions, to make our problem a statistical problem, we need a lot of data. And there is no substitute for real observations in real nature, despite all these laboratory experiments. And so, as I mentioned last night, much of my effort these days, in addition to taking new observations with the data we have and doing laboratory experiments to understand them, I am putting quite a lot of effort into the next generation of observations through an effort called SZ4D, subduction zones in 4 dimensions, to properly instrument across the system at the level that we need to take a statistical view of the problem. Okay, I'm going to stop there. Thank you for the questions you've had, and I'm hoping there are some more. I don't know. That's the mystery, isn't it fun? It's a couple spots. So it's at the down dip and also the up dip end in Nankai. So it's thought that there's a big locked region in the middle, which is what ultimately is going to rupture in a very, very large earthquake. And right at the edges of that is where slow slip and tremor happens. There's a very similar observation, at least at the down dip end in Cascadia. Interestingly, at the transition between the locked and the creeping section of the San Andreas in Parkfield, there's a similar set of observations. So it appears to be something that happens in this sort of transitional behavior when you're not fully locked and you're not fully creeping. That's the best I could do. There are thoughts that might be pore pressure related. There are thoughts that might be material property related. It basically says that you don't quite have enough strain energy stored up locally to keep propagating into and accelerating into a large-scale fast rupture, and so that you're able to exhaust some of that energy through creeping all the time, but there's a little bit of locking there, so you're not just steadily creeping. Another question? Had a nice lunch together. You asked plenty of questions then. Yeah.
My question is, more earthquake propagation regionally, what's the impact of distribution of the faults themselves, size, location of, these unknown faults and fractures? We talk about distribution of energy and strength, but is that all on a single fault, or what's the
No, yes, no, okay. Yes, there are distributions of faults themselves. We've done some work on looking at the distribution of secondary faults and also fractures as a function of distance from main shocks. Heather Savage and I did that quite some time ago, and then Alba did a redo of it much more recently. And what Alba did was take a look at the distribution of secondary faults on in this damage halo around each fault, and then ask the question, well, how does that influence the probabilities of faults of hazard on those secondary faults? And you can sort of spread out your hazard analysis so you're not only thinking about the probability of an earthquake on, say, the San Andreas, but anywhere in the system that way. So that's I thought that was a very useful exercise she did. So those secondary faults exist. They are, in fact, well-defined distributions. They are likely telling us something about the stress field in the near field of a large earthquake. Why they take the form that they have, don't know. But they're certainly an observable.
So maybe more fun question. You started off saying that we can make earthquakes, right, our microseismic ones, but those are always by mistake. We'd rather not trigger those most of the time. Have you ever thought about controlled experiments? Somebody gave you $10 million.
It costs roughly 25 to 30 million, so yeah, I thought about it.
What experiments could you do to answer what big outstanding questions related to
Um, I think we would love to do such experiment. Heather and Jamie Kirkpatrick ran a workshop to think about it right before COVID, and I think it sort of was a bit of a casualty of COVID that lost a little energy, so to speak, but with the idea of looking at actively induced seismicity at an experimental purpose. What you could do if you knew it was coming and you knew you could unravel what stresses are making the earthquakes. You could actually put the pore pressure monitoring down there so you could pull together the pore elastic strain and ask, is it that? Is it just the pore pressure? Is there perhaps a slow slip element? And there's been a lot of recent work suggesting that if you shove fluid into a fault, you actually get slow slip as an intermediate step on your way to making a real earthquake. And I think you could totally unravel that with an active experiment. To some extent, that was done in a mine in southern France by Avoak and Kappa and Guglielmi and co-workers. I thought that was a really important experiment. Very, very small scale. I go big, go better. But in particular, I think you would also ask the question of magnitude predictability is another really important question in this field. Can you anticipate, based on the pre-existing stress field, what size earthquake you're going to have? Nobody knows the answer to that. And then finally, you would also ask the question of what sort of precursory activity and warning signs would you get? So I think they're all important questions. I think none of those can be answered without an active experiment. The great question is where. There are parts of the world that seem not to be particularly bothered by injection-induced earthquakes. And so maybe going back to them and saying, hey, we're doing it on purpose is no problem. It's generally been a problem with funding agencies to be associated with this project.
I thought your experiments very interesting, at least to me. So how does the real Earth, if we replace that with the real Earth with viscosity, across lateral viscosity and or whatever, it's going to change, may change the composition of that experiment. So in other words, you have, I guess, two slabs with sands. What if those material of the Earth becomes real Earth with viscosity and other stuff? How would it change your composition for that experiment? I'm not a reviewer of your paper, of course.
That's fair. So it is meant to be a model system, not a simulation. And it is purposely not Earth materials. Because Heather Savage across the hall from me has a triax, a lab where she squishes real rocks. And we have a friendly competition about the fact that I play with plastics and rubber and she does actual rocks. The value of doing the analog material is that because it is soft, you can have an experiment that's literally this big and have a confined rupture. Whereas for a rock, that would be equivalent to a 3-kilometer large fault zone. And so that's why we're doing it this way. Also because it's transparent and we can make a movie, which we can't do in a real rock. So there are advantages and there are obviously disadvantages. We are not capturing accurate frictional properties of actual rocks. We are not capturing any combined deformation of viscoelasticity and elasticity. But what we are doing is isolating sequences. And I think for the issue of how history and geometry interplay to create a stress field and observable phenomenon, this is the right experiment. If you wanted to ask a different question, this would not be the right experiment.
But there's also a lot of geological heterogeneity there, a lot of faults.
So, you know, it's kind of like a chicken or egg problem, like, why is the tremor there trash? Like, is it the fact that it's the geology or the earthquakes? I don't know, what do you think about it?
Definitely a chicken and egg problem. I think I'm going to go out on a limb and say the earthquakes are trashing the tremor. Now, why the earthquakes are so many there is possibly related to the triple junction and some pretty extreme concentrations of stress geometrically, but I don't really know. But once you have that level of seismicity, it is really hard to have synchronized, well-behaved tremor and slow slip. I used to give this talk with Cascadia instead of Nankai, and the Nankai is prettier, so I switched to Nankai, but it's the same systematics in Cascadia. The problem with Cascadia is basically 3 zones to look at. And one of which is southern Cascadia. Yep.
Is it right that the 4th dimension here is time?
Yes.
I wonder, like, it's very interesting to look at the power law distribution of the size that you showed. How much of it do you think comes from the concept of so-called self-organization? Have you ever thought about using some theory like self-organized physicality to look at the power law distribution of maybe time intervals of those extreme events like avalanche or even earthquake?
I've been dancing around those words the last year or so, and self-organized criticality. I would welcome some theoretical help in how to actually use that theory, because I am aware there exists a theory of self-organized criticality. I don't really see how to get from here to there other than to say, hey, look, there's a well-organized distribution, and it's probably related to the overall heterogeneity organization by a frictional system. But actually quantifying why that distribution and not some other distribution, I'm not sure how to harness that mathematical machinery, but I suspect there's something there's a there there.
Questions? Okay, well, thank you very much.